let's review. Um, so we're talking about just a very simple motion, uh, and you saw it before in Calculus 1, but it was by design or by necessity. It was only one-dimensional, so either you moving one horizontally or vertically. And then there is a you might see a variety of motion, but by choosing different situations, but they're not happening simultaneously, and so the patterns are fairly simple. So this is very simple, actually. If you think about it, just combine the two together, and so since they do not interact with each other, the horizontal and vertical motion, then it is literally two versions of Calculus 1 problem. Okay, so just for convenience, we make certain changes, and those are, for the most part, for example, we name the variable for time t rather than x, and the x and y are taken for the spatial variables, and so location. And then if you want to proceed, then you'll have z also, vertical location or whatever you choose for it, and you can have motion in any space of any dimension, as long as well, there is really no restrictions on the dimension of it's not going to be a physical space, but rather something man-made space. I don't know, prices or other characteristics that change in time, but it's so manageable. And as long as we can progress from 1 to 2, which what we do, then progressing to 3 and 4 and beyond is easy. But it will have to wait until Calculus 3. So we're just doing 2. And looking at the simplest motion, going all the way to Newton, a thrown ball in the air. Okay, so the idea, if you really look at it from the point of view of physics, you would have to ask a question: what are the forces affecting the ball? But really, it's not. You can look at it more in, like an exploration, and just examine what you do care about, what you have learned from Calculus 1, and that is what matters is acceleration. So acceleration matters, and then if you know acceleration, you find the velocity for velocity location, and then you'll just see what's going on. And turns out that it appears there is a vertical gravity, vertical acceleration. So whether it caused for gravity, or is it gravitational force, or is it just acceleration, doesn't really matter. We're looking at a purely hypothetical way, and then see if it matches the reality. So we have an acceleration, 32 feet per second squared, and meanwhile the horizontal, there is no horizontal acceleration. Okay, so then we carry out these two operations separately. Treat the two variables separately, f double prime, f prime. That gives me the last formula, our motion, vertical motion with respect to time. So location as a function of time. Sometimes it's you can see it written just like this: x equal. I'm sorry, that is actually y. Y is equal to negative gt squared over 2 plus ct plus k. Okay, and that is the most general vertical motion under gravitational acceleration, or whatever acceleration is. It really it doesn't make any difference whatsoever. It's just a good example of something that you can match with the reality. The only thing is that the acceleration is constant. So if you can think of another acceleration of force that is constant, no matter where you are, no matter what time is, then you will have the same exact analysis. So that's what makes it mathematics, not physics. In the meantime, we see the simpler situation, horizontal motion, the acceleration not only constant, it is 0. So that's why the computations give us a linear function. So x equal to mt plus n. Okay, so that's the second equation. Even though that last equation is our interest, but really all the three, and certainly quantities matters. Not only the x equal to this, but x prime, that's y prime, you might be interested in the velocity. Okay, so for example, So the number one question would be to ask is where the ball hits the ground, and that is certainly you're going to need the last two formulas, as a matter of fact, for both horizontal and vertical motion. You're going to need these to find where this object hits the ground. But then the second question might be, what is the velocity when it hits the ground? Okay, so then you're going to need all of the let's say 4 formulas: the 2 for location and 1 for 2 for location and 2 for velocity. Okay. So these are our formulas. This is a special case that I want to consider. The hill 200 feet, shooting directly straight horizontally at 200 feet per second. The initial velocity is here. The formulas for x and y we have written. In fact, I would like to change that notation so that we would be slightly more comfortable. So this is y and this is x. Okay, so as a function of time, so there is no, we have, except for g, which is 32 feet per second squared, is the only, everything is specific. So all those constants are gone. We specified them based on the initial conditions, and now that is our location. Location is a function of time. Horizontal, separate from vertical. So the question might be then, so how far does it go? The cannonball or a ball. And so certainly the picture tells you the whole story, but mostly common sense. So you don't really know the answer until you actually plot these. Or you can remember some things from Calculus 1 and before, and just remember that y that function for y is quadratic with the so before we plot these, the y as a function of t will look like this. Well, so if we look at the graph, at the formula over here, what it is simply a quadratic function, and that's what you learn early in calculus or pre-calculus. What happens to functions, or specifically a parabola, when you do certain things, and those certain things are adding to 100, but first multiplying by this number. Okay, so in fact, well, let me split it into 3 steps. This multiplying by g over 2 first, multiply by negative sign second, and adding 200 last. Okay, so these are the 3 steps that you do to a parabola, and then the result is a parabola that is still a parabola. And what does the parabola look like? Well, so t squared multiplied by g over 2, what does it do to the parabola? This part. If we multiply function by some number, positive number, what happens? It vertically stretches, and since it is 32, all right, or 16 rather, it will be literally stretching vertically. Okay, so that's a parabola, becomes slender, and then you multiply by negative sign, which does what? So start with this, then stretch, and then you multiply by negative sign. What does it do? Flips it upside down, and finally add 200, shift up. So like this. So that is indeed the result. It is, as you can see, we have no horizontal motion, so which means that the y-axis remains the same, so it's all centered on the origin. So we can easily say that this will be, well, the graph parabola. So this parabola is, you can ignore it, but really it's still there. So you know that the parabola then crosses the x-axis, y-axis at 90 degrees horizontally. Okay, so the other one, so literally things only start happening at t equals 0, and that's the actual solid graph on the right. On the left, I have this dashed curve, but you can certainly interpret it how, well, you reverse time or something like that, and then whatever happened. might also, you probably can make sense of it as well. So we certainly want to look at the whole parabola just to know that wouldn't be any confusion about where the parabola is centered, and it is centered on the y-axis, so the symmetry of the situation remains. So it starts at 200 as we expected, otherwise it wouldn't make sense. We also see in this picture we see a lot of things that are in the description. We also see that it is the tangent line is horizontal, so it starts at there is no y component. This is not, by the way, this is not what we see if you, an observer looking at the shot, he's not going to be seeing this because, for a simple reason, because this is the horizontal axis is the t-axis. So it is time, and the time is not something that you can see literally. But once again, starting at 200 points, no vertical component to the velocity. This is which would be simply the slope. So the slope is 0 over here. So that's all visible in this picture. But really what we care about is the whole picture. So we need also the t as x as a function of t. Fortunately, it is a very simple one. It goes like this: slope, a straight line at slope 200. And only combination of these two gives me the graph. Not gives me the graph, gives me the path. So this is graph of x as a function y as a function of t time. This is graph of x as a function of t. So these allows us to solve all the problems that we want, including this one. Well, it is the problematic is to read too much into it and say right away that is why we see a parabola. The parabola that we see, an observer, a side observer sees some kind of a parabolic motion, but it is really not visible from this picture yet. You have to demonstrate that. We need to demonstrate why the path is a parabola. So once again, this our motion is made of these two functions. One of them is a parabola, the other one is not. The path is what would be traced by an object, however, in space. So in other words, really when we speak of a parabola, we speak of that parabola located visible in space. So this is space, this is time, and this is time. This is space, but only part of it, and this is also space, but part of it. Really, to see what's going on in space apart from what's happening in time. So like in the dark, and if that cannonball maybe has some, I don't know, maybe it's a rocket or something, and then there is a light, then it creates a trace in the sky, and then everybody knows it's a parabola. So why is it a parabola? So how do we demonstrate that it's a parabola in space? Well, we're talking about then parabola. It is really not. It is really about simply dependence of y on x. So that's what it means. Of y on x, and so in other words, when we're saying that, what we're saying is that the graph of y is a function of x is a parabola, which simply means that y depends on x quadratically. Okay, and then where does it come from? How do we express y in terms of x? Well, these are the formulas. So this is a y and x depending on t, two formulas. We want how y depends on x, one formula. So how do we make 1 out of 2?
Say t equals x over 200.
And
then plug it in.
and then substitute it. So solve for x. I'm sorry, solve for t. So t becomes x over 200, and substitute. So that eliminates t. It's like a system of two equations. You may have seen them before, and you just solve them for one of the variables, and you end up, instead of two equations, you have one equation. So substitute, let me substitute. So I have then y is equal to negative gt squared over 2 plus 200. It is in fact equal to negative g over 2, and here I have my 200, I'm sorry, what is it? X over 200 over here. X over 200 squared plus 200. Okay, so that already does it because, so substitute. Eliminate t. Eliminate t, and you're left with x and y, and it is a direct dependence of x and y. You can certainly simplify it, so make it a function out of it. So you have, what is it, negative g divided by 8 with a bunch of zeros, x squared plus 200. So this is, so once again, it's a parabola. Once again, it is, we know how to sort that out. So once again, there is stretch, there is a flip, upside down, and 200 up, and the parabola will, once again, it will be kind of slender, but still the idea is still the same, like this. Okay, so once again, there is a because of the symmetry, once again, because of the symmetry, we realize that the tangent here is 0. Okay, so we start at 200. Y starts at 200. X starts at 0. And then what we have described is visible in this picture. That this the slope is entirely horizontal, which means there is no y component as intended, as it was intended from the beginning. And the only thing that remains now, we can point out what we're looking for. This is what we point out. If we want to know how far it goes, this is how far it goes. So we also have demonstrated that it does hit the ground at some point. So there's really no challenge here, other than just now go ahead and solve the problem. It doesn't really, let's see, do we really need anything but these two equations? Do we need the third equation here? It certainly is a nice one. It proves something very important about motion. Follows, just like we demonstrated in this class, that the area of a circle is pi r squared. The length of a circle is 2 pi r. So that's things that you know from early high school or middle school. And then we demonstrated that indeed it was not demonstrated, we proved it mathematically that it's indeed true. That's another example. Everybody knows that the object is flows by parabola. Now we demonstrated that it is indeed true mathematically. Okay. So do we really need this in order to find how far it goes? So this is what we're after. We are after a certain value of x, and I suppose we could take this formula to find this location. So how do we find it? Yeah, y equal to 0, so y is equal to 0, so we end up with a straightforward quadratic equation. In fact, simpler than quadratic, because of our choice of initial conditions. The quadratic equation is especially simple and has this nice symmetry, so we just solve it. Solve for x. And so what is it? Well, there will be two, by the way. That explains why quadratic equation will produce two answers, even though only one of them may make sense. So it will be, what is it, 200 times 80,000, if I'm not mistaken, all divided by g square root. Okay, let me make sure that this is correct. So 4, 1, 2, 3, and 3 divided by g. Really? Let me check. So 4,000. 4,000 divided by 32. Let's see. I have a different answer here. So it appears that it's about 125. Why do I have something else here? Probably lost some zeros. My answer is 700, roughly, and this one is 125.
Be over the square root of g.
Square root of g. Okay. Thank you. Oops. Okay, so let's confirm that. Okay, 40,000. 4,000 divided by what the hell is square root of 32? It's about 6. So it's close enough. Yeah. So the if you do it with a calculator, the answer is more precise, and it's about 700. So 700 feet then. So 200 feet height, initial height, 200 feet per second is the initial velocity horizontal, and it will go 700 feet. Okay. So what is the difference if the situation changes? Not a lot. So the plan works out. So that's the end of the problem solved. So what would be different if this is the example that we were looking at. What would change if the only thing that we can really change here is that the velocity is not necessarily entirely horizontal, but there is a vertical component to it. Okay, so what would that do? Not a lot. So if we have a vertical component to it, so maybe like this. Okay, then then there will be what? There will be an extra term here. Whatever the vertical component of the speed will be multiplied by t. So remember that extra term over here. What I'm talking about. This one, this term that takes care of the vertical component of the initial velocity. So in other words, the difference will be it will be still quadratic. The difference will be, however, that it will not be centered at the y-axis anymore. So it will be off either this or that way, depending on whether we're shooting up or we're shooting down. Okay, so and then the end result is not complicated, because all is going to happen is you'll have an extra term over here, especially. So it will be a quadratic equation that cannot be solved by simple manipulation, but rather you need a quadratic formula. So quadratic formula is you might need it if you're solving anything more complicated than that. But it is purely algebra and nothing else there for us to worry about. One more issue is that I mentioned before. So since we know, so the drawback of this, the choice of the way we chose to solve the problem this way, the drawback is how do we answer the question, what is the velocity at impact? So totally related question. And so if you're throwing a ball, you want to know how hard it hits the ground, or whatever the object you're throwing at, or a cannonball hitting a wall of a castle. So you need to know the velocity. So how would you solve it? This is the the formula for the velocity is here. For the vertical velocity is the picture, in the blue at the very top, and the blue for the horizontal component is this. It's very simple. It is simply the horizontal doesn't change. So that part isn't hard, but the trouble is to apply the first formula. It's not a function of x, right? So it is a function of t, as a matter of fact. So then to apply the formula for the velocity, it's not only we need to know where it is, which we just found, but we also need to know when. Okay, so the question becomes, to answer this one, we need to answer first when, not where. So this is where. We found x, y is equal to 0, so we totally exactly know where it hits the ground. You can test it as long as there is no a lot of air resistance. If you were able to, what is the indications of a low effect of air resistance would be an object that is dense. So actually, Cannonball is pretty good in that respect. If it's very heavy, and so maybe has some aerodynamic shape, so it is unaffected by a lot, but by air. So you can test it. It has been tested with just that. Nothing more complex. But we still need to know when. So that suggests that another way of solving the problem that we just did solve would be to answer that question first, and then with that you know when, and then you know not only where but also how fast. Okay, so so this is how fast. Both of these questions are answered based on the question answering first when. So t, and that's what if or the question could be also how long did it take to hit the ground, and you still need that formula. So it's not complicated. Let me run out one more time. We have our equations, and so to find out, I still set y equal to 0, but not with the formula that we just derived, but with the original formula for the location. So y is equal to negative gt squared over 2 plus what? Plus 200, yeah. Plus 200, we set it equal to 0 and solve, but not for x, for t. Solve for t. So then, so y is equal to 400 divided by g squared. Okay, so yeah, so it's approximately 3.5. 3.5 seconds, that's approximately how long it takes to hit the, it's not a y, it's a t right here. So t we found it takes about 3.5 seconds to hit the ground, y equal to 0, okay, and then to find substitute now into the equation for the vertical velocity and the horizontal velocity. So for the vertical velocity is my y prime is equal to gt, okay, that's it, sorry, negative gt, because the initial vertical component of the velocity was 0, so it's simply negative gt, and gt we just found, so it will be negative g times 3.5, which is approximately, I don't think I have that data. About 112, I think. Negative 50, yes. Negative 112, so it's going down, so it's negative. And x prime is equal to simply it's constant. It is 200 per second, so it remains 200. So then you can draw a picture roughly when the ball is hitting the ground. It is going 200 that way and about 100 horizontally. So it's going, what, roughly 2 by 1, like this. So under this angle, if you want to know what the angle is, not only how fast, but the angle of the impact will be like this. So once again, 100 down and 200 horizontal. Okay, so so that solves the other problem, and you can solve any problem that you can think of with these equations. So I just want you to see that the problem is being also important. At the same time, it is extremely simplified. So not only because of the air resistance that we ignore, but also the scope of the situations is limited. One thing to expand this situation is very easy, and that is ask ourselves what's going to happen if we are shooting a cannon on the moon. What's going to happen to the equations? G will change. That's it. Nothing else. So everything else is exactly the same, right? So in other words, we did solve the problem for shooting cannonballs on any planet imaginable. We wouldn't make any difference. However, if we want to go into extreme, and then to start to think about situations that are less common, it is for example, if the motion, if the gravity is might be directed in a under a different angle, and so maybe there is no up and down or something like that. Maybe there is another planet, or maybe our planet has this kind of shape. If you can imagine, this is our planet, which means that if you're shooting a cannonball, there will be a gravitation. That force goes both up, both down, and horizontally. Okay, so it's not going to make our life any harder mathematically, even though physical situation is totally hypothetical, and I guess would not be especially applicable to any real life situation. But if you want to explore the how far you can go with this, you can tweak the analysis a little bit and see how far what you can get. And this is the simplest probably situation that you can imagine. Then when like I said, there is a gravity. Not only vertical but also horizontal. So what difference would that make? Nothing over here. Then under H, which means horizontal, this will be some kind of a non-zero number. So in other words, possibly different gravitational constant or rather acceleration, and then you just go on with the same computation. So then there will be quadratic motion with respect to x and with respect to y. Okay, so exactly this formula that we just derived over here for the vertical motion when there is a acceleration under gravity, there will be a almost identical formula with possibly different g for our motion along the horizontal as well. So quadratic for horizontal, quadratic for vertical. If you try to guess, what would the result be? What kind of motion is that? So you can think mathematically, you have quadratic formula for horizontal and quadratic for vertical, and then, or you can think about, if you want to think physically, what if, like I said, there's gravitation both ways? What would be the path? Or, I mean, there are actually many possibilities, but what can you think of? Well, the point is actually what I'm driving at is really not to try to figure it out by guessing, but that this has all been done. The problem that we solved, it was done by Newton and a lot since him by a lot of people, more complex problems. But what they didn't have, they didn't have computers. So we don't really have to think hard with formulas or try to rely on intuition. to guess the answer, we can just write up formulas and let the computer do the job. So that is what we're going to do now, and then we'll start by reproducing this problem that we solve analytically in Newton style, and we'll just do it with the computational style. As we saw some of it before, so let's do it, and then we'll tweak it and see if what kind of new results we might discover, because computers can do what we tell them. So anyway, so this is the situation. The initial velocity, velocity horizontal vertical, initial position horizontal vertical, and let's just. Let me just find that. Okay, so sorry. Okay, so let's. Okay. Okay. So what I'm going to do is I will do what amounts to integration, numerical integration. So what we just did a minute ago, or rather we did it last time over here. We derived these formulas. These are the formulas. We derived them by integration. Okay. So we knew the acceleration, and then we derived the velocity, and then we derived the location. Okay, so now we're going to do the same thing, but for the numerically. So it will be, the answer will be approximate, but that's good enough for us. Okay, so what I'm going to do here, I will put, so this will be my t time t is my time. Okay, so then what else do I need? These will be the columns time. Then there will be it will be x double prime. So that will be my horizontal acceleration. Then horizontal velocity. Then horizontal location. Okay, then the vertical acceleration, vertical location, and vertical velocity, vertical location. Okay, so all of these will be dependent on t. So starting with say 0. Okay, so I'll put, as I do, I put the step of my increment of time here with 0.1, say, and then so I will increment time by this much. So it will be equal to the previous plus R3C. R3C1. Okay. Okay, so these are the increments of time. And now I will only know, as a problem that we're solving, we know the initial accelerations, nothing else. Okay, so then this is the column that I will know. And let's just go with the way we did it. Just the problem we solved, the horizontal acceleration is 0. Okay, so this is horizontal acceleration; it remains 0. But let's derive that's just the data that we provided. We'll change that later if we want it more complex. But then what happens to how do we derive the velocity? Okay, so from acceleration, how did we derive velocity without integration? We assume that during this short period of time between 0 and 0.1, the acceleration remains the same. So all I have to do is, well, let me, so it is equal to initial velocity. Our initial velocity was what? Was it horizontal velocity was 200, so I put it here. Okay, and then what I do is I compute, then I increment my my velocity based on the acceleration. So if the velocity is previous current velocity 200 is known, then the next velocity will be 200 plus not 200 plus, but rather this element plus what? So the time passed between point 1 and 0, that's the time increment. And then what I do is I take the current acceleration and multiply by it. So let me just write it for you. So it will be the current acceleration times the increment of time. So let me just put time here again. So it will be h r3c1 r3c1. Okay, so once again, see what's happening, how we compute the velocity after this short period of time has passed. I take the previous velocity and add to it my acceleration multiplied by time. That's the meaning of acceleration, if it is constant. Okay. Fortunately, this one will work out whether or not it is constant or not. Okay, so in this particular example, the acceleration is 0, so the velocity remains 200. Okay, now the location starts at 0, and how do we get location from velocity? The formula is the same. Okay, so the formula is the same, so we take the previous location and add to it velocity times time. Okay, velocity times time is what how this all stuff works. Okay, so this is the formula. Take another look at it. Computation of the next location based on the current velocity. How far did I go during this time period? It is simply time times velocity. Okay, so that velocity is in red multiplied by the time interval, which is purple on the all the way on the left. Okay, so that's how far we went from the previous position. Okay, and as you can see, that works out. We go every 0.1 seconds. We move on by 20 feet. 20 feet at a time. Why? Because the speed is 200. Okay, so that works out just fine. And now I do the same with the for y. Except I need to make some changes here. This one. Hold on, what happened? Over here. Over here. Okay, let me change this. Okay, and same thing here. No, wrong. Okay, so let's see. Let me try to put the actual data. So 0, there was the initial velocity, vertical, but the location was initially 200. Okay, so I need to fix. The acceleration is negative g, so I'll put here negative 32. Okay, and it remains the same. Okay, so does it make sense? Yeah, look at it. What's happening? So my vertical acceleration remains negative 32, and based on that, I compute the vertical velocity, and the vertical velocity starts from 0 and then goes down, negative 33.2, negative, so it's become more and more negative. We are accelerating towards the ground. Okay, and then the location, as you can see what's happening to the location, it is slowly decreasing. So we start at the altitude of 200 and then slowly going down vertically, but faster and faster. It is, as you can see. Okay, so let me check the, okay, so that works out. Okay, so that is everything that's happening that we need to know. How much, and then I can expand this all the way as much as I need to find out where things are going. So this after 4.45 seconds, this remains pretty much the same. This is the how far it went. But what has happened is, look at it, this is not interesting anymore, because as you can see, the last column is our altitude, and the elevation is negative 160, means that we already have passed through the ground. Where did we pass through the ground? So here somewhere. So that's roughly the time on the left, followed by the vertical acceleration, velocity, and location, followed by the horizontal velocity, location, velocity, acceleration. And then the last one is, as you can see, at 3.4 seconds, we are at 9.6 feet above the ground, and at 3.5 seconds, we negative 1.6 feet, which means that we are below the ground. So some way half between these 2 points, we do hit the ground. So if we say that it might be very close to 3.5 seconds, is a fair estimate. So this is where things are happening. Okay, and we can try to. So let's see if we is this what the answer that we got. Time. The time is 3.5. This one is 3.5. Indeed, which we did analytically, we discovered the same result now numerically. We have also discovered the speed of the vertical and horizontal. The horizontal is still 200 as expected, and negative 1.8.8 is our well, actually, probably this number is better. I think we just take this one as actuality. So as you can see, negative 112 is our vertical velocity. So as you can see, if we just by examining the data, we have an approximate answer to the same question without doing any integration, but rather just doing certain algebra. So you can once again see at the formulas that we just used here. We just progress from one to the next, assuming that is the main idea of such an acceleration. Such an analysis is that there is no change of velocity during that time period, and there is no change of velocity, and there is no change of acceleration during that time period as well. So you do everything incrementally, and so if the acceleration is known, then you will know what your next velocity is, and you progress from row to the row, and then similarly you're getting the next location one at a time. Okay, so that's how you can do it, and of course it would be a shame if you do not actually take advantage of the. Okay, we're out of time, but so next time we'll plot the graph.